Okay, so the title of my talk is Creep Turns Linear and Narrow Ferromagnetic Nanostrips. So let's start with the first word, creep. Creep is the motion of elastic interfaces through weakly disordered media. So one example that probably everybody knows is the geological fault lines. There, two tectonic plates move alongside each other, and in this way the interface in between moves quite slowly also. Then for the motion itself, it's characterized by little jumps or bigger jumps, and times when there is no motion at all in between. So the jumps we know as earthquakes. A little bit more common are actually then 1D interfaces through 2D media, and there we have the examples of fluid wetting, fluid impregnation, or the growth of bacteria colonies. My business is actually magnetism. So let's consider this magnet. We have one big magnet here, and it's magnetized all in the upwards direction. So this configuration leaves a lot of energy in the stray fields. And as you know, nature doesn't like a lot of energy that can be minimized. So let's look at this configuration. Here we have two magnetic regions magnetized in opposite directions. And this leaves only a little bit of energy in the stray fields. But more importantly for us, we have in between these domains also an interface called a domain wall. Then if we apply an external field, then you see that again this region magnetized in the same direction as the field is energetically favorable, and it wants to grow at the expense of the other region. So we can move this interface, the domain wall, to the right. Now, for all these different systems, the motion as function of the driving force can be divided into three regimes: a creep, a depending, and a flow regime. And we are interested in this creep regime because there the motion is dictated by the subtle interplay between the temperature, the driving force, and the disorder in the system. And for all the different systems I talked about, including the magnetic ones, this motion is dictated by a universal creep scaling law. So in the figure at the bottom, we have put data on a set of axes in which this creep scaling law shows up as a straight line, and you see that indeed the data lies on these straight lines. Then another example, here we have a magnetic thin film. The left side in white is magnetized towards you, then the right side in black is magnetized away from you. And in the middle, again, we have this elastic interface, which is a domain wall. And for very wide films, again, we see that the creep scaling law is observed. However, when we look at thinner films, narrower films, then we see a deviation from this creep scaling law. Here, this green line is no longer on the straight line. So we could ask ourselves, what causes this? Maybe it's no longer a 1D interface through a 2D medium, but is it maybe a zero-dimensional interface through a 1D medium, which would mean that the domain wall can be described as a point particle or a rigid object. Okay, further question. Why would we be interested in these narrow nanostrips? This is because they have technological applications. For instance, here in the racetrack memory, which might be an alternative for your current computer's memory, the data is saved as the direction in which the domains in such a nanostrip are, in which direction the domain walls point, the domains point, sorry. So the questions we want to answer: first, is the domain wall a rigid point-like object moving along a 1D energy landscape? And secondly, which scaling law does it follow? To this end, we will have a look at this system. Again, we have a narrow nanostrip, which is magnetized in two oppositely pointing directions, here in red and blue. And in the middle, we have a green domain wall. And the disorder in this system is included by considering a polycrystalline material. We will have a look at this system from 2 points of view. On the one hand, we will look at it with full micromagnetic simulations. And there is no assumption made on the domain wall structure, because there we are simulating each individual atomic moment. Well, its dynamics then from a very low level point of view with micromagnetic theory. And on the other hand, we will look at it with a 1D model. which does assume that the domain wall is a point-like object moving along a 1D line. And this 1D model gives us an equation of motion, which looks a bit terrifying at first, but actually is quite easy to interpret. So first we have a mass term, which is proportional to the acceleration, a friction term proportional to the velocity, then a term related to the disorder in the system, a term related to the temperature, and then two terms related to the driving forces, which can be a current or an applied field. But very important for us is that all these prefactors can be quantified exactly, and there is no fitting going on whatsoever. So if we have a look at the results, here in black you see the solutions to this equation of motion, and the data points show the results from the micromagnetic simulations. And you see there's a perfect overlap between both results, which leads us to conclude that indeed the domain wall can be described as a zero-dimensional object moving through a 1D line. Also, here at the right, you see 5 different paths that the domain wall could have taken and which led to this data point. And you see as function of time that indeed the domain wall can be pinned for a very long time, and then with discrete jumps it moves forward, which is exactly the motion of the earthquakes I talked to you about earlier. Then secondly, which scaling law does the creep follow? Here in the inset we have tried to fit the universal creep scaling law to our data, and you see that it's a complete mismatch. It isn't even the right shape. Then on the bigger figure we have plotted the velocity divided by the driving force as function of the driving force, and we see all these straight lines here to the left, and this leads us to conclude that there's a linear relationship between the velocity and the driving force instead of this creep scaling law. We also verified this experimentally. So here on the left you again see the example I showed earlier, where the straight line indicates that the data follows the creep scaling law, and this is for the very wide thin film of 650 nanometer. Then next to it we have the narrow thin film, so really the nanostrip of only 160 nanometer width. And there you see that, again, we have the linear relationship as opposed to the creep scaling law, which could be fitted to the data from the wide strip. So the questions we answered are that first, the domain wall is indeed a point-like object, or could be considered as such, moving along a 1D landscape. Despite its complex structure, we verified this by using micromagnetic simulations, and we validated a 1D model description with it. And secondly, as opposed to the universal creep scaling law for 1D interfaces through 2D media, we found that there is a linear relationship between the driving force and the velocity, and this is also in correspondence with experiments. So a lot of people contributed to this result, and I would like to thank all the groups whose logos you see here, and also you in the audience for listening.
Time for questions.